That's good. Numbers of sales are great. All right, good evening, everyone. Welcome to the February evening lecture organised by the IET Central London Network. I'm Rimesh Patel, a volunteer for the IET Central London Network, and I'm going to be a host for today. We're a group of volunteers that get together once a month to organise engineering events that support the IET's mission, which is to inform, inspire, and influence. Just like today's lecture, which is on the topic of electric air racing. We've got a good amount of registration, so thank you so much for being available to attend today. Our first speaker is Jeff Zaltman, the CEO of Air Race E, and our second speaker is Richard Glassock, a Research Fellow at the University of Nottingham. Now, before we get to our pioneering speakers, we just have a couple of house announcements to make. So firstly, as a data privacy notice, we're letting you know that this session is being recorded and the audio and video features have been disabled for all delegates within the Zoom platform. Secondly, we've enabled the Q&A box, so please make sure you put your questions for the speakers inside the Q&A box and we'll get to them towards the end of the session. And we've also enabled a chat box into which we're going to place the CPD certificate. So you'll be able to download the certificate of attendance for today's session if you require it. And finally, as I said, because we're recording this session, we're going to make it available on YouTube and also our blog. So please do look out for that. And now with housekeeping done, I'm going to hand over to the CEO of Air Race E, Jeff Zaltman. Thank you, Jeff.
Thank you very, very much, Rimesh. Let me pull up my presentation here. Apologies. But I'll let you know that I'm going to be telling you a little bit about Air Race E. Then I'm going to hand over to Richard, who's going to talk a little bit more detail, especially about the engineering side of things. And then he's going to pass it back to me and I'll give you a little bit more of an update on some of the other activities, in particular, how this talk relates to some of the teams that we're working with. So let me just start off with what's sort of obvious, but it's very important to just kind of say it in a nutshell. Air Race E is the first electric airplane race. So there's a really historic, really momentous activity. What we're really trying to do here is to take air racing and aviation into the future by converting it to electric. What we want to do is, of course, create a platform. It's a development technology platform, really for the acceleration of the electrification of aerospace. So really, big stuff here. And you could say, kind of, you mentioned Formula E here. So probably the simplest way to put it really is that we're doing for aerospace what Formula E is doing for automotive. So most of you are probably very familiar with the electric car races, Formula E, and they've launched another one, Extreme E. We're doing really very much the same thing as they're doing in terms of the concept and even the business model, certainly the mission, but we're doing it with airplanes and we're doing it for aerospace, but it all is interrelated in e-mobility in general. And at the end of the day, of course, we want to create a really thrilling fan-based motorsport. So at the end of the day, it's going to be an exciting race as well. To give you a little idea of this exciting race, a little bit of flavor of what we do, I'm going to ask Rimesh if he could just play a quick video, a very short video to give you an idea of that.
You know there ain't another girl like her in the city. She looks so good, but she ain't so pretty. Ain't another girl like her in the city. Yeah, you know she looks so good, but she ain't so pretty.
Okay, so hopefully that came across okay. It's as we said, a very, very exciting sport, and it's kind of important to mention. There we go. What you saw there was coming from a format we currently do. It's an air race called Air Race 1, and it's a form of Formula One air racing. That's the format. So it's actually a sport that's been around for over 70 years. Really, really successful race format. It's super exciting. It's got 8 planes lining up on the runway all together at the same time, drop the green flag, and they take off. And they're racing from the start. Climb to about 10, 15 meters above the ground, up to 450 kilometers an hour around an oval circuit. The first one to cross the line wins. So, it's real pure motorsport, really exciting. And the reason that's important is because Air Race E is basing itself very much on the format of Air Race 1, or this Formula One air racing, but of course, readapting it or adapting it for electrification. So what you saw there is very much how it's going to look on the electric side. Now, as we said, it's very much a motorsport, real pure motorsport. You guys will all be familiar with the fact that motorsport throughout history has always been used as a very successful foundation for developing products, developing technology, bringing products to market, and innovation in general. And air racing, though not as well known as some other motorsports, also has a rich history and is very much part of the fabric of air racing. And air racing goes back over 100 years, started in France in 1909, and has taken on different formats, different disciplines throughout history. But it's always been very, very essential, and also used just as an automotive or land-based motorsports, used in innovation. Perhaps one of the more kind of famous examples is the Spitfire, which of course was one of the most famous and successful warbirds from World War II. That actually began life as an air racer. It was built for the races in the Schneider Trophy in the 1920s. So that actually was designed for the mission of racing before it was repurposed for battle. And that's, again, what we're really trying to do is to hone technology for other purposes, of course, in outside world. So, of course, we're a thrilling fan-based sport. So it's a motorsport, it's very exciting, but we're really trying to also do something very, very meaningful. So meaningful to the world, meaningful certainly to the aerospace industry and transportation. But not only on the development of technology, that's of course the kind of pointy edge, and that's what we're really trying to do. But not only that, but also infrastructure. For example, airports, of course, how are we going to have more electric planes flying, electric aircraft flying, if we don't have the infrastructure in the airports and the facilities and the operational know-how to support it? So we're very much have that in mind, and general city infrastructure and cross-pollination of technologies across transportation. And of course, we want to shine a spotlight. By being a sports competition, of course, we have access to the broader audiences. So we want to shine a spotlight on the efforts that cities and other stakeholders and technology companies are making to make aviation cleaner and really to address the decarbonization issues in the world. Our organization is actually the world leader in organizing international airplane races. So where airplanes race directly against each other, the purest racing, we've actually organized more races than anyone else in the world. In fact, we're the only organization that does so. It's on an international basis. So we have all the ingredients, we have all the components and the know-how and the experts and everything that goes into making a race. Of course, what we didn't have was the technology side. So, we're really fundamentally opening that up to the broader market to say, look, we need the industry to come in and start developing this technology with us to make the racing exciting and, as I said, meaningful. So we've done that, and we have a lot of success. We have lots of different companies involved. They're involved in different ways. we refer to this as our kind of stakeholder ecosystem, because some of these are suppliers, supporters of teams, partners, some of them are teams, of course, some of them are sponsors and partners of this series. Obviously, University of Nottingham here is a very important partner of ours. A couple of others that you can see here, which are clearly very critical partners, are Airbus, is our founding partner. They came on board as a founding partner a couple of years ago, and they've done a really great job of helping us get off the ground. And ANSYS, which is really taking a very hands-on and kind of integrated role with the teams, helping them using their world-leading simulation software to really develop and help speed up the prototyping process for the team's development to get them to the starting line so that they're going to be ready by race day. And they've been a fantastic support using their software with the teams, helping them use it as well. Having said all that, it's really important to stress that ARACE-E is an open platform. So it's, the concept is that we're the hub of the electrification effort. So what we want to do is make sure that every stakeholder, every company in the industry can have a place, can find a place to actually do what they do inside ARACE-E. So it's not exclusive, it's very much open. And these are, you see here on the screen, these are some of the areas that we're going to be testing and looking at and really trying to develop. And I think Richard's probably going to talk a lot about some of these areas that they're exploring as well. And perhaps it's important to also mention, I like saying, ARACE-E is a real world mission, right? So it's a race. There's winners, losers, there's an objective, and you can measure your performance, success and failure, but you can measure it, and it's really important that we have this real world mission of a race to be able to push the limits of innovation. And I think, as you all know, like when we talk about motorsport, it really is competition that drives that innovation. So we got to mention the rules here. It all really fundamentally comes down to the rules. So what we do is, as I mentioned, we have our rules based on the Formula One air racing rules, which are those other races we organize, and just changing what's necessary. So of course, there's a lot of safety procedures and a lot of expertise and a lot of good rules that have been baked in there for 75 years. So we don't want to change all that. What we want to do is convert it to electric. So we have some new rules, of course, which are added in. One of the obvious ones is the power limitation. We have set a 150 kilowatt max continuous power. There is an opportunity to increase that by 25 kilowatts for 30 seconds in a boost during the race. But that's the basic power constraint to the engine. The race is only going to be 4 laps. So while a Formula One air race is 8 laps, the electric is going to be 4 laps. Each lap is 5 kilometers. So the duration, that's 20 kilometers of racing plus about 10 minutes of reserve on 20 to 30% battery. Now, we don't dictate how much battery they use or how it's how it's configured, but we do make sure, and there's ways we can talk about that we make sure that they have enough battery, of course, at the end of the race, et cetera. So there's other different safety things that we have to incorporate. This slide's really just to give an idea of, kind of some of the other rules. There's rules pertaining to the wing area, visibility, things like that. Of course, some of the configuration of the powertrain, there's rules around that. The image in the bottom right there is really just kind of showing the grid pattern. So there's, I guess what we have, as I should mention, we have technical rules, which actually are the formula for building the airplane. And then there's procedural rules, which are the rules for running and operating the race. So yeah, I'm gonna come back, I think, in a moment. So what I'm gonna do is I'll hand over now to Richard. He's got some really exciting, all the juicy stuff you wanna hear about. And then I'll come back and tell you a little bit more about the teams and our future plans, and go from there. So Richard.
So my name is Richard Glassock, and I work at University of Nottingham as a research fellow. I've been there about 5 years now. Originally from Australia, and I've done some other work in Europe. And so it's a real pleasure to be invited here to speak for the IET, and thank you very much to you guys and to Rimesh. So let's carry on and see how we go here. So yeah, we have a real interest at the university in developing electric systems, electric propulsion systems in particular, and we have a fairly good footprint into the aerospace industry at large. And to show some of the skills and technology that we develop, we wanted to have a demonstrator platform. And I met Jeff about, I think, 3 years ago, and we started to discuss how we could go forward, maybe together, and we could do our demonstrator in the university and help Jeff's ambitions and aims as well in the racing, because we could see how that would really work as a brilliant way to demonstrate electric propulsion technology for aircraft. So you can see there, Jeff actually had the airplane flown into our local airfield here at Nottingham and handed over, and we brought it into the laboratory where we have a lot of good facilities to work on this kind of vehicle. You can see, one of the first things we had to do was pull the engine out, the old thermal 4-cylinder aero engine. And just a little picture there, I've got to rush through quite a fair bit of stuff here, but one of the first jobs we had to do was to actually model the aircraft into CAD. So we actually had a laser scanner process to bring that up into a CAD form so we could start working on the mechanical integration side, how we fit all of the components into the aircraft where the engine used to be. I've put up there just a couple of references to YouTube videos, and you can take a quick note of those. Obviously, I didn't want to try to play too many videos online. They can cause a bit of trouble, but I've got one a little later that I'll play for you. So we wanted to phase the project in two main stages, so phase 1 and phase 2. The first phase, which we are nearing completion, is phase 1, where we use mainly commercial off-the-shelf components, and we do the integration, and we form a baseline for the aircraft to operate and for everyone to learn about what's going on. And we're pretty happy to share pretty well all of the details of that, which I'll be going through later. And then the phase 2 would come after that, when we start to develop a properly optimized, specialized system that's suitable for the Air Race E, but also, as I'll mention later, can suit some other future industry and commercial applications. So it's really important to just realize that we're doing this in two main phases, and what I'm showing you tonight is really all of phase 1 stuff, but it leads into a much more bespoke and custom development of electric machines and power electronics and the integration of those with an emphasis towards being suitable for Air Race E. So the key components of this can be broken down into the electrical design, and that includes the battery system, mechanical system of the design of the system, so that we can integrate everything into that particular aircraft. Obviously, all the other management issues for procurement, and they're not to be underestimated. They really do take up a great deal of the life. And then we do want to have this aircraft operational, so we have to always be considerate of airworthiness requirements, how it's going to be flown in the future, under what jurisdiction, and what are the requirements of that jurisdiction. So we're working with several partners. You can see a little picture here. It's an early one of how the initial integration scheme was going to look. You can see how that modeling of the aircraft in CAD was useful for that. And in order to build this airplane, in the university, we do research predominantly into the electrical machines and controls and the engineering overall, but we're not aerospace manufacturers, and we're not aerospace specialists in terms of putting together aircraft. So we partnered early on with a local helicopter maintenance engineering company. It's just down the road, and they've been extremely helpful, East Midlands Helicopters Engineering. So at the moment, the airframe is located there, but we are doing the rest of the work in-house in our laboratories. So as Jeff mentioned, there are the basic Air Race rules. We've got a maximum power, which is a very good limitation to work to. You've got to have a baseline somewhere, and that looks pretty good. I just want to mention here that our installation in the first instance is not going to be 150 kilowatts. We're baselining about 80 kilowatts because we estimate that's approximately the power that the airplane we had that we're working with came with. We know the Cassets actually can fly quite easily with that amount of power with a standard engine, but it's not all about power. So if you look at the basic relationships, you don't need to have a huge amount of power to still win a race. Obviously, you want to have the maximum power you can, but if you have less power, it doesn't mean to say you're going to be uncompetitive, because there's a lot of other factors that go into getting around that course quickly. And so I just wanted to highlight there about the relationships between the drag and power, how that works out. So one of the reasons why this works at all is because the race time is relatively short, 5 minutes. One of the problems of electric aerospace in general, obviously, is energy storage. Precludes a lot of the bigger aircraft for longer range, but really suits what we're trying to do here. And we can develop that technology, which then enables and enhances the future development of commercial aircraft, which obviously are typically going to require more flight time, although some of them could get by with 5 minutes if you're just doing short hops, of an air taxi, which I'll talk again a little later about. And then, you've got to have a backup in reserve. There's always a requirement for reserve. So we baselined about 80 kilowatts for our aircraft as a maximum continuous power for 5 minutes. And then a reduced power setting so we can organize a landing, cruise and circuit. And that's what we're basing the overall design on. So types of motors that are currently available off the shelf, or mostly, more or less, just going around here, just this is a sample, this is not exhaustive, but this is a YASA motor up the top left. That's one that we actually decided to get because it's a UK-based company supplier. I think it's mostly designed to power land-based equipment like cars and so on, but it suits, and I'll talk more about that later. These AMRAX units here, Slovenian, they're used in a lot of electric aircraft projects going forward. They're not, there's nothing wrong with them for that purpose. There's pros and cons for all of these things. This Safran unit here, which I saw in the last Paris Air Show, very, very nice machine. Safran, obviously, specialist aero company, very well optimized unit with lots of good features internally. Has the power electronics internal. It has not much need for external cooling, but super expensive. About probably 8 to 10 times what we were budgeting on our project. And then there are some that were formerly Siemens motors, which are now Rolls-Royce motors. Very, very nice equipment. Also being used in some projects. Again, it's just a little out of our league for our university at this time, and I hope that they will become on the market more generally as we go forward. There's one up here on the top right, which is more interesting, I guess, and I'll discuss in a moment just one of the backgrounds that we have in electric propulsion for racing. But this here is a motor that was completely designed and built in-house at Nottingham for the e-racing motorcycle. So one of the students, PhD students, did this as his main thesis, really. Very, very high power to weight ratio, and a very, very good prospect. Not quite suitable for the aircraft, because one of the things we've got to look at is, do we have a direct drive or do we have a gear system? And we prefer to have a direct drive if we can. And this motor here is designed to run at a higher RPM. And there are trade-offs, obviously, with that. So there's a broad spectrum there of types of motors that are suitable, would be suitable for air SE, and we just selected the more convenient one for the time being. So other things you need to put this system together. Obviously, we've got the airframe, a nice basic Casset unit, very well established aircraft, quite a simple construction, quite easy to modify. We've taken the engine out and the fuel system out. And so we put the electric motor, we have to replace that in there. The inverter, which drives the motor, takes the DC current from the battery, makes it suitable for this brushless permanent magnet motor. Unfortunately, typically it's not for everyone, but in this case, it needs to have a liquid cooling circuit. So you have to have a heat exchanger, you have to have a pump, you have to have piping and some control of that equipment. as well as on the inverter. So the inverter also has a separate liquid cooling circuit with a pump and a heat exchanger and piping. You've got to have a battery system, which I'll discuss in a moment. The battery system has to have a management system, BMS, battery management system. We want to have pilot display, so we've got a fully programmable unit here from Motec, which does a pilot display. They also provide an ECU, which from a motorsport background, but a computer which can manage and control all of this stuff for us in a programmable way. And then obviously a pilot interface for the throttle controller to replace the throttle to give a power control. And down the bottom right, obviously, we've got to have a charging system. So it's all part of the system that we're putting together. So as I mentioned, there's a background in Nottingham of electric racing, in particular on the TT0 superbikes. And we had very, very good success over, I guess, about 10 years at places like the Isle of Man, Pikes Peak, Assen and others. And so the technology for this bike was all developed in-house, including the battery system. So this is using a pouch type lithium polymer cell stacked into modules with a proprietary, a custom in-house designed circuit board that connects all of the tabs, puts bus bars between them, carries other stuff like thermocouples and voltage sensors for each cell with outputs. And then you stack them all up and you put them in the vehicle. And in this case, the vehicle goes really fast and actually very nearly took out the Isle of Man a couple of years ago. It came second to a Mugen Honda and it beat the other Mugen Honda. And I think the budget was something like 50 times less or 100 times less. So that's some of the background that enables us and encourages us to go ahead with the aircraft project. So a little more detail in the battery system. We didn't want to modify this aircraft very much in the first instance. We just wanted to do a very simple conversion and a basic one and a safe one. So we simply used the space already available within the cowling mold line, took the fuel tank out, put in batteries where the fuel tank was, and obviously where the cylinders were in the engine, we have room there within the original cowling. So we used that space. We made boxes that are made of a proprietary composite material that's very, very fire and heat resistant. And we'll be laying these battery packs within those boxes. And it's not really efficient to do it this way. The other thing is we use the original cassette engine mount and to bolt the motor to. So it's not highly optimized, but it's secure and a good way to begin the whole process. So in each battery container, you've also got to have isolators, and you've got to have fuses and connectors and so on. So here's the picture of these boxes, the way they are practically laid out. You can get an idea of the scale of the batteries compared to the original cowling there. Also the particular type of battery cell we're using, that's a single cell there. We're putting about 170 or 180 of those together in series. There's a pallet of them you can see right there, so that we've got a good stock of batteries. And that's ongoing now. The battery packs are being created right now. This is just a very, like a bit of a sketch really of the battery system with some, they're not quite precise numbers, but just kind of pretty close kind of numbers about how that works out in terms of the overall mass of the cells. Once you get the other parts of the battery system in, it really adds up, and we're probably looking at over 100 kilograms for the battery pack, but about 70 kilograms of cells, and we should get about 14 amp hours or 10 kilowatt hours from that pack, and that's enough to do the initial tests that we want to fly with, and on the grounds tests. I doubt it would be good for racing, although, as I said, this is for 80 kilowatts we're baselining, and all of the other factors come into play. So we would think that the racing aircraft will want to have the full 150, and it'll have to have a larger battery pack. There's some information here about things that are going on in terms of standards. So, we're using a commercial charger at the moment, but the whole standards for electric aircraft are being drafted and developed by various organizations. This is just one example that's currently underway. for the charging system. And there's any number of other standards that need to be developed and then provided so that we can get into commercial application for these things. So a little detail here on the actual installation. As I said, we wanted to keep it fairly simple and not modify the cassette very much. So the red framework here you can see is the original engine mount that like Continental Low 200 bolts up to. So we wanted to keep that, and we had the motor. The motor just comes, as you would have seen in the picture earlier, with no outputs really. It has an internal spline shaft. So to get any other loads than torque onto that, you have to provide some other structure, mechanism, spindle shaft. So we've got a spindle shaft here that we designed, which takes a carry out of the spline from the rotor of the motor through a bearing set and then into a propeller adapter. We didn't really want to have to mount too much external framework around that. It's a relatively large diameter motor already, considering the original cowling we've got. So it just barely fits in there. And if we started to put too much mounting around the outside, well, we were going to have to change the whole front cowl. So instead we run the loads through the motor. So obviously can take some reasonable loads. It's got to be mounted at some point somewhere. But we had to be very careful to spread those loads out and make a nice stiff bracket and structural loading system to carry all the propeller loads through into the original structure. And then we've got an adapter bracket here. So this is steel truss, takes straight to the original engine mount and then adapts it into our electric motor. So again, it's not strictly optimal. This is all extra mass and complexity and cost, but it is a good way to get the job done and quite reliably. So it's also very modifiable. The other design intent was to allow future different motors. So if we want to change the motor out, we've got the bearing assembly here, the spindle shaft, which can be mounted to the airframe in different ways, and we can run different motors on it. We could also, if we wanted to, we could run a geared motor. So we could just put some kind of a pinion here or a gear here and run a parallel motor with either a belt drive or gear or whatever. So we did some structural analysis. We actually outsourced a consultant just to reality check for what we've done in-house. So structural analysis just within normal FEA to show everything is really within the limits. And we went to a stressing of the Part 23 aviation standard, which gives you the kinds of loads that you should expect given a certain power and RPM. So that's what we've got as it's built. I then took all of those components to our friends at East Midlands Helicopters, and they did the final assembly of that onto the airframe just to ensure that all of the modelling that we'd done in the CAD was suitable, was going to fit. So it worked out quite well. And you can see here, this is almost a year ago actually, but there's been some development of the airframe, but we've been mainly with the current world situation, we've been very well delayed, and we have now got the motor and the inverter into the lab, and I'll show you that coming up soon. But you can see how it fits in there. It's just as I was explaining, the structural layout of it, where the battery packs fit. We had to do a little modification. It's no big deal just to put a blister around it. Keeping the batteries in a rectilinear kind of shape just really helps. So it was more worthwhile just to have a corner poking out than to try to keep all of the battery compartments molded to the original fuselage shape. And then you can see the other pack there just ready to be fastened up. So it's a nice, neat installation. And in fact, if you wanted to, and if you had to, you could easily bring this airplane back into the original form without too much trouble. We don't expect to have to do that. I think this will end up being an electric racer for quite a long time. So into the lab. So we took it off the airplane once we established that it fitted properly, everything was right. And we put it onto our dynamometer within our labs. This is a normal thing that happens in the Nottingham labs. Lots of different motor designs and power electronics are tested. It bolts up onto the dyno, onto this big bookend here. You can see the cooling system just we have to run some, desk fans really just to try to emulate a little airflow around that heat exchanger. This picture here, you see we've also measuring the torque. So we've got a continuous independent measurement of torque. We can also derive torque out of the load that we're putting on it with the load motor. And also I think the EASA also provides that information. Now, hopefully this little video works. It just shows you the system running. Yeah, so very quickly, it's running on the dyno in the lab, and we can load that. We can load the load motor. It's fully adjustable, programmable, I guess, by software. It's a big machine that the load motor, weighs probably 10 times or so the weight of the motor we're testing. And my colleague, Dr. Alessandro Galassini, is in there most days these days, working on it, just fine-tuning the parameters for both the load and also the EASA, so that we get a very good understanding of the characteristics, including the thermal characteristics, before we put it onto the aircraft. And we can do practically all the testing we need to do in this lab. And then once we put it onto the aircraft, we're very confident how it's going to perform, and we put the propeller on it, we start ground testing, and we ensure that all the system that I showed you before, including the higher level controller, is programmed correctly. There's a lot of variables, so you could imagine. Anyway, that's yeah. So you could imagine the variable of how quickly does the motor respond to an input. So the pilot throws a lever, as like a normal control lever, and you can actually adjust how quickly the motor speeds up. And you want to do that because you want to limit the torque at some point. You don't want it to try to come right up to full torque, full power instantly, or within, less than a second. You probably want it to build up over 3 seconds. So that's what we're doing in the lab. And we're also looking at this kind of stuff here, which is quite important for the particular cooling system that we selected. How is it performing? So we can run it at different power levels over different times. And we get obviously readouts of the temperature of the inverter. He's called a converter here, but so this is the inverter temperature at those different powers over different times. This is the temperature of the stator in the electric motor, the EASA. Again, different power over different time, and in the rotor. And so there are some limit temperatures, and we've got to be careful about that. And you can see for a start, and this is fairly early results, so we haven't done much tweaking or modifying. We're seeing some relatively high temperatures start to occur at only 50 kilowatts over this time period. Now that's not a real problem. We can go higher in the temperature, but we know we need to go higher in the power. And the way it's building up here, I think we're going to probably re-examine the cooling system. We've got people who can do that, model it. We can easily change out the heat exchanger. It's quite a small one at the moment. And we know that when it's in the aircraft under different operating conditions, that's going to change as well. But this is the fundamental basic stuff that we'll get right in the lab, and then we'll move on to developing it as we do the ground testing in the aircraft and fine-tuning everything. And ultimately, once we're flying it, we're getting this and a lot more data to come out of it, and we can fine-tune the whole system, everything of interest, everything about the safety of it, but in particular the reliability of it, and the performance of it. So I wanted to move on. I think we're doing fairly well for time. Just to tell you a little more about our facilities and how we're going to take this into the phase 2, how we're going, the changes that are occurring in the university, the investment that's happening, so that we're confident we can develop an entire new bespoke propulsion system for this type of aircraft, and actually larger ones that I'll mention in a moment. This is a new building. So the lab that I showed you just before is in one of our older buildings on the campus. There's an entire new building being constructed. It's actually finished now. People are starting to move into it. You can see 3,500 square meters of labs. It's significantly larger than what we're working with at the moment, and it's all new and with the most modern equipment. You can see where the funding there is from it. this just gives you an idea of the layout in this new building. I think it's approximately 5 or more times the amount of space that we're currently got. And I can't go into all the details. You can contact me or any of the other academics if you want full details. The kinds of machinery that are going to be in there, the kind of power, we want to be testing and developing electric machines, that is generators and motors and power electronics, all the way out to about 20 megawatts. So, you know, we're testing this you know, roughly 100 kilowatt motor at the moment. You can see that there are motors actually in our labs at the moment at 4 megawatts, but for bigger aircraft applications and other transport applications, it will be going out to 20. So a little bit of from the year before last. So some of the other background on the project, we went to Dubai. We showed an aircraft there, which was a conceptual aircraft of the same type, Casset, but you can see here it's running a contra-rotating propeller system, and there's some very good advantages in doing that. In this case, you can see these are actually the same type of Yasa motor, not quite the same model number, but practically the same. There's 2 here, they're stacked back to back. They've got an internal shaft that runs to the back motor, external shaft to the front motor, so you can run these contra-rotating propellers. The very key advantage of electric propulsion, actually, and particularly on a small aircraft like this, if you're running very high power, being able to have a completely balanced torque output is really important for the handling of the aircraft. But it's got some interesting characteristics for larger aircraft and you know, for efficiency. And there's a number of reasons for doing this, and it's one of the things we will probably look at when we go into our phase 2 development. Shall we or shall we not go to a contra-rotating? At least I think we're going to make it contra-rotating ready, so that, you know, we might have one motor on our aircraft running single rotation, but in the future, if you wanted to put it on a bigger aircraft, you could have a contra-rotating system. This is an example of that. So this is a project I am working on, and what we want for the project and what we want for ARAC is to yield results that are interesting commercially. So I've done a lot of research and work with skydiving companies. I've got some very good partners who have run very large skydiving companies. And one thing that, you know, that they are interested in is electric propulsion for a number of reasons. And a key one is actually performance and cost. So obviously reducing fuel costs and the emissions that come from that. But with electric propulsion, it's really interesting. You can really improve the performance. So in this example here, we've taken a Cessna 182. Now this is Photoshop. Okay, we haven't built it yet, but we are planning it. And we know that the motors that I just showed you on that cassette will fit into this aircraft. And then when we run some numbers about how it performs as compared to the original power plant, we're very, very pleased and maybe a little surprised. So with the original power plant, to climb to a good jump altitude, so we're talking about 12,000 feet, maybe 14,000 feet, even a turbocharged version of this aircraft could take 25 minutes or more to climb to that altitude and use quite a lot of fuel in doing it, and the running costs associated with that. So if we put in electric motors, we can put in a lot more power, and we can control that via the contra-rotating. We don't get control issues out of it. We may modify bits and pieces of the airframe, but there's practically zero residual torque out of this propulsion system. So we run a lot more power. We can run maybe 300 kilowatts, whereas the original aircraft was around about 200. And we then calculate the climb rates, and we can see it can climb maybe in 5 minutes to the same altitude. So the cost and time saving, and you know, where you're getting the energy from, etc., is very compelling. This is a picture of another potential layout, which is more complex, but having twin motors on the wing, you can get some efficiency advantages out of that by decreasing the disc loading, increasing the propulsive efficiency, and again, you can run a lot more power and climb a lot quicker. So there's some very compelling, you know, future industrial applications for this work we're doing in ARAC. Going to a larger scale, just very quickly mention another project I'm working on a larger skydiving aircraft, a 4-ton type aircraft. It's a hybrid, so you can run a gas turbine and you can use a generator system. You can run series and parallel hybrids. the types of motors that we're looking at developing, 150 kilowatts, as a basis, maybe you could develop it out to 200 or so, would fit very, very nicely on this 4-ton aircraft, having one on each wing, a smaller gas turbine engine than you would otherwise need. And again, the performance numbers start to become very compelling, as do the economics once you start to investigate it. So it's all about what we are doing technology-wise for the future. Here is a broad spread of other commercial applications, some of which you may be familiar with, but they're popping up all over the place. The industry is full of this kind of stuff now, and for very good reasons, from regional airliner concepts, commuter business type aircraft, whether they be pure electric or hybrid, vertical takeoff and landing air taxi type aircraft, improved propulsion efficiency, having distributed propulsion with a lot of electric motors that have, it's possible to mount electric motors in this configuration, whereas it's really not possible to mount gas engines. And you can see them all over the place. There's literally hundreds of them, maybe thousands by now. I wanted to particularly mention this project because it's a UK-based project for a very compelling design for a regional, sub-regional pure electric aircraft. You can look it up, you can contact these guys. It's a well-developed concept. I mention it because certainly on a smaller version, the 9-seater, the power that they're planning to put through these electric fans is going to be possible with our development if you stack the motors. So you stack 2 or maybe 3 of the 150 kilowatt motors, and you've got enough to fly this this aircraft here, and potentially also with contra-rotating fans. So I want to draw it to a close there. I just want to show you this other example of a concept aircraft, which is my favorite. I've got a bit of a background in gliding and in hang gliding in particular. And this is a feasible aircraft because of electric and hybrid propulsion. It would have 2 propellers, two electric motor systems, and gas turbines, so hybrid systems here. It happens to have an open top as a glider. That makes it really interesting from the recreational and my hang gliding background. If you've not been into the air with a proper open top, open air aircraft, then you're missing something. I wanted to do it with more people, so here's room for 6 people. But you can turn the engines off, and then when you need power, instantly available by the electric. You've got no warm-up, no startup sequence. It's just instant power, and it opens up a whole lot of new roles and missions for aircraft. So I'll leave it there. I'm hoping to get some questions, and I'll hand it back to Jeff to close it out.
Okay, thank you very much, Richard. Let's see if I can share my screen again. Yeah, great stuff. I have to say, I always am really enthused when I hear Richard present and talk about all the different projects that he has and the different technologies and advancements that he's making with our project, with the race plane prototype. Is fascinating, and they're doing really excellent work. And it's nice, like I said, it's nice to see how it fits into the portfolio and how all these technologies interrelate and they're interdependent with each other. So it's really exciting to be part of that. And the University of Nottingham and Richard's team have been an invaluable partner for us over the past couple of years to be developing it, but not just the hands-on stuff, but the strategic and the kind of brainstorming aspects of it. So thanks for that, Richard. Okay, my next segment is I'll try to keep it short. I'm going to talk a little bit about the teams. I'm not going to go into any of the detail that Richard has. I think that was pretty expressive. I think you got a really good sense of what goes into this. So I'm just going to touch upon them really briefly. This is just a quick snapshot of all the teams that have registered. Now they're in varying degrees of readiness. Some are fairly early stage, some are quite advanced. You're going to see some of these teams, many of them actually, flying this year. So you're actually going to see test flights and qualifying runs of these race planes this year, manned and full on, full power, ready to go. So this is going to be a huge year. 2021 will be really massive, and it's exciting because these teams come from all over the world, and they're really capable. So let me just, like I said, shine a kind of quick spotlight on several of them. This one is Team Tor from Norway. Now they're approaching this from a retrofitting paradigm. So what they're doing is they've taken a really capable formula race plane, existing formula race plane, and then from changing it from the firewall forward, as you can see in that diagram, converting it to electric. So this is very much kind of the standard kind of concept we have of people taking an existing platform and then focusing on the powertrain. What's exciting about this is that this powertrain that they're developing on this platform for the race is a powertrain they're going to use in an actual aircraft they're developing for production. So it's going to be, a powertrain is going to lead directly to the powertrain that's on the aircraft that they're going to be fabricating. So that's exactly what we want to see coming out of AirAce. Scramasax is our French team, and they're doing a great job as well. This is also another example of retrofitting. So they're working with, as you can see in the bottom right there, it's a picture of a Casset 3M, that's their plane. And that's been flying, that's been testing in the conventional way, and now they're going through the process of changing the powertrain. What they're doing is using all off-the-shelf components. So they're kind of going for the keep it simple, philosophy, and try to bring in and really just focus on optimization and efficiency, and really just get in there and start racing. This is Team Magpie from Switzerland. Now these guys have a completely ground up design. So this is all their design, not just the aircraft, but the powertrain itself as well. You can see the diagram here, they're actually distributing the battery throughout the wings. So that's distributed in a different way than, it's not the firewall forward mount that the previous ones have used. And obviously it's noteworthy there. They've got the V-tail, which of course takes away a surface area and can decrease drag. So these guys are a really exciting professional team that also have ambitions in the aircraft production afterwards. Team NL are obviously Holland, the Dutch team. This is another ground up design. So this is actually all ground up. It's kind of obvious there that they're also using a contra rotating system. So, 2 coaxial motors, very similar to the one that we had displayed in Dubai that Richard had pointed out in those images. They're looking at a contra rotating system for, better power management, balance out the torque, which, as you know, in electric can be quite intensive. So Team Mobius, these guys are out of the US and Texas, and they're really concentrating solely on, the real focus is producing motors, this particular motor here. So they're in the race to develop the technology that they also want to on-sell eventually as a product in the marketplace. What's exciting about this is they've taken out 85% of the steel from the motor, and they say that this is the first ever paper and 3D printed motor. So obviously that brings with it many efficiencies, and that's an exciting development that they're working on. So lots of things come out of this series, lots of different technologies, different approaches, different, like I said, it's an open platform and it's an open concept. As long as you meet the formula rules, you can kind of connect those dots however you see fit, which allows for massive amounts of innovation. But we're not just about tech. Just quickly, we've said it before, it's a spectator sport, it's exciting. We're going to be on TV all over the world. This is going to be reaching audiences live and in media throughout the world. We're going to be starting racing in 2022. So we're already going to be racing next year. We're right now doing a bidding process with different host cities around the world. Fantastic amount of interest in that and participation in that process. And we're going to be doing some qualifying races this year. Sorry, not races, but qualifying activities, qualifiers, qualifying events. And eventually the plan is to grow to 8 races in a series on an annual basis in all parts of the world. We've been garnering tons and tons of media coverage. That's really great to see that when we have a vision and an idea and we're stepping forward, and all the people that we're talking about here, putting in so much effort and resource into making this happen. And it is great to see that that's getting recognized. Obviously, even just this group today, so many people attended and signed up for this IET event, and we're super grateful for that. So it's exciting. So we're getting out there into the media and really trying to share our experience of what we do with as many people as possible. So here's another quick video. I hope it can come across with the imagery, but it's just a short minute just to give you a little bit more insight. This is actually from our Dubai exposition, so I'll stop sharing and see if Rimesh can tee that.
This is a really exciting moment for us. We're here at the Dubai Air Show to showcase the first ever electric race plane. So racing around an oval circuit around pylons, all 8 planes together, passing, weaving, winding. So it's pure motorsport and real racing.
We help building up a whole ecosystem around electrification. It can be picked up by our urban air mobility or even scaled by our bigger Airbus airplanes.
Okay, great. Thanks for that. So yeah, that's, let me share the screen again. So that is, again, a snapshot of what we did in Dubai. It's, you know, I wanted to put that in there because it's, it shows again the attention that this is getting, but also Airbus. I mean, it was fantastic for Airbus to host us there and to really bring us into the family of, you know, projects that they have and showcase it to the Dubai Air Show. It was interesting that, you know, when we were there, the news media, a lot of the local news media turned up and said, you were the most shared news item of all, you know, the whole show. So we had to come out and film this. So it really taps into a lot of different interests and touch points. So yeah, well, listen, I think that more or less wraps it up. I just left it here as a couple of kind of testimonials, I guess, and a few of our partners. You know, we are really grateful for everyone who's been involved. We really hope that everyone who's listening can find a way to come out and be involved in what we do. And you know, we're, like I said, an open platform and hopefully going to be growing in a really big way. So we look forward to, you know, having more touch points with you and perhaps a more intimate way of meeting as well in the future. So thank you very much, and everyone can feel free to contact me as you wish, and I will hand it back to our host. And thanks again.
Thank you so much, Jeff. We're now going to go over to Matt to do Q&A.
Okay, so thanks everybody for sending through your questions. There's been absolutely fantastic series of questions coming through from everybody throughout the entire presentation. First question I'd post would be to Richard. There's been a lot of interest about batteries and motors and the space that's required for the Red Bull, for the batteries and the motors. But if we just cover the batteries for the moment. So one of the most upvoted questions was around the development of the new battery designs, and whether you were involved with development of new battery designs, or whether they're battery units adapted from off-the-shelf available designs. And then subsequent to that, a question around whether supercapacitors could be used for fast delivery of power during the races instead.
Yeah, sure. It is obviously the key, really one of the main features that has to be got right, not just for racing, but for commercial and industrial application. So we do develop our own battery packs, but it's not really the main ambition for what we want to do. We've done it on the bike because we wanted to have a racing bike. We wanted to have control over those items, and then also to learn and do the research on them. We don't really do cell level stuff, although we've got a chemistry department, and we can do fundamental research in cell chemistry, but we don't try to build them. And in terms of the packs, there are quite a number of commercial suppliers who do contact us actually, and we talk to them. And I don't want to get into particular technologies or other. A lot of aircraft are using cylindrical cells, for example, and there are pros and cons. Typically, I think you'll find that the commercial aircraft will end up using cylindrical cells, but it's not a done deal. There's still work ongoing on a whole range of battery technologies, and we know that the battery energy density is really the key problem. Power density and the relationship between the power density and the energy density is an interesting relationship. So, in selecting our cells, that's one of the things we look at. We want to have a pack that will provide the best performance for our race, but other applications for longer range aircraft, will have different requirements. I think the supercab thing is really interesting from the point of view of the racing and maybe in general. Like if you've got an application which has a very distinct kind of load cycle, such as eVTOL, some of them have a very high power requirement for a very short time, and then they can ease it off into a cruise segment and then require very, very high power again for a short time. So I think there's definitely a role for supercapacitors in a system like that, where we're not developing that yet. We may be interested in it, but that will come later. So at this stage, we're not working on that or doing it, but it's clearly part of the overall mix that needs to be considered. And maybe for the air racing, some competitors will come in there and look at it and do it. I think it's one of the great things about having a format like this, where people can innovate and test their equipment and put it up head to head. So I'm hoping that answers some of those questions. So while I'm at it, I guess the cooling system, I didn't go into that too. So some battery systems require active cooling. Some of them can have passive cooling. We haven't investigated that a lot yet. That's part of the program, is to investigate that. We may vent the boxes. I didn't mention that the boxes have to be vented at some point because the failure case of a fire is going to be a lot of gas expanding, so that has to be vented out, not in a fully enclosed vessel. And that also then starts to look into, okay, you can flow air through the pack on the discharge. How much do you flow through? On the recharge, you can flow through. It's easier to do that on the ground potentially, because you have a ground assisted thermal management system that plugs in and plugs out. So there really is a real lot of innovation and technology to look at in the whole process. But at this stage, we want to get the machine operating, taxiing around on the airfield for starters, and then get it in the air and do some test flying. And we want to do that this year. And I might just mention while I'm at it that I forgot to mention, we have got a very keen prospective industrial partner looking into coming on board, who will be very, very good at doing all of that final integration, airworthiness, and operations. So we're actually quite confident that we'll get this thing flying in the summer.
That's great to hear, because that actually answers one of the questions, one of the other questions, which was how long until the prototype is up and running? Yeah, well,
we had planned for it to be flying some time ago, but various things get in the way. But I won't mention the particular outfit just at the moment, because it's not finalised. But they are very, very, very good at what they do.
Okay, brilliant. Well, there are lots and lots of technical questions, but just jump into a slightly different area. One of the other interesting areas was the Red Bull Air Race series and how this fits in. I think this is more on your side.
Yeah, no, definitely. So, I mean, Red Bull Air Race, obviously they had a great, probably 15 years of running a really exciting sports competition. So they did a fantastic job, especially of taking air racing out of the kind of, sidelines and really saying, hey, this can be used as a promotional platform. It can appeal to mainstream audiences. So Red Bull did some good things there. The format is very, very, very different. So Red Bull, of course, did a single plane time trial, an aerobatic time trial against the clock. So it was one plane against a clock in a slalom routine. we race all our airplanes directly against each other. So it's a really direct competition. So we're really trying to compete directly on the technology as much as the racing circuit. So the format's very different. I think that the concept, the model, let's say, is really different as well, because Red Bull, of course, did it as they should for a promotional sponsorship activity to sell energy drinks. Whereas we're trying to do it really as something for not only for audiences, but for the industry as well. So it's you know, we have, ours is open, you know, anyone can come. It's not hired pilots. It's, you know, it's an open sport. It's a genuine sport. Yeah, so there's a lot of differences. You know, again, Red Bull, of course, has done a lot of great things in that area, but they also stopped the Red Bull Air Race a year or two ago. I think it was 2019. They ended their series, so they have a great place in history and in the halls of air racing. But right now, you know, we're the leading racing series out there, both in the Formula One and in the electric. So, yeah.
That's really interesting to hear. On a slightly different note, there were a decent number of questions also asked about certification. So, whether the CAA is involved with this, whether type certification needs to be gained, how you arrange with local airports or airfields for this, and what sort of involvement you have with local governments. So if you want to cover a bit more about the regulation side of what you're doing, that would be great.
Yeah, Richard, did you want to talk to that, or I can talk to that?
Well, I think I'll just say in the first instance that we are in contact with the LAA, Light Aircraft Association in the UK. They have the authority delegated to them from the CAA to look at how these aircraft are operated. They too are very, very interested in learning more about electric propulsion in broad terms. A lot of their membership will be interested in electric aircraft going forward. So they're not certified aircraft, not to what we normally think of certification, you know, FAA or EASA Part 23 or anything like that. So it's a lower level, but it still has to be given a permit to fly, and that's arranged through in the UK LAA. Different countries have got different jurisdictions, but once that's handled and given, which it will be by due process, then the types of airport that it can fly at, it's more a restriction on you know, how busy those airports are, and you know, what the local climate is, I guess, in terms of is it a suitable place to run a very short endurance aircraft. But so, yeah, and Jeff, what do you think?
Yeah, so exactly. I mean, each country, as Richard said, is going to have its own system for analyzing this. In the US, they have the experimental class. In the UK, it's called E-conditions. It's actually a relatively new system for doing something similar to experimental class. And every country is going to have its own. So what we do is we have our teams, really the onus, the responsibility is on them, because they're designing, they're doing the building process independently. It's up to them to get the certification in their country to fly and operate the aircraft. Say certification, again, there is a big difference between a certified aircraft that would be used for commercial purposes and these planes, which will always remain either experimental or permit to fly, because it's going to be just for the use of the pilot. In the race, it's always going to be a different purpose. So it does away with 99% of the regulations that would apply to an eventual commercial aircraft. But what is an interesting element, I think was also part of your question, Matt, was that's one step to get the airplane certified as airworthy. But then you've got to bring it to another country, put it back together, and then race. And that's a whole other set of permissions. So there's permissions that even in that other country, which you have to get them to sign off again on the building process. Now there's a lot of reciprocal arrangements, depends on where we go, and that's all very much part of the process. And that's something the series does. That's something we do. It's not down to the teams. We take that, we go get that permission. But it's another step, and it's quite involved. And then you've got the permissions from the CAAs of the world for the race itself. So, you know, a race is technically illegal. It's not permitted. We have to go get permission for it, much like an air show would. So then we have to contact the civil aviation authorities and go through lengthy processes to explain how we do it, what our procedures are. And as you can imagine, it's motorsport, it can be dangerous, it's aviation. Safety is absolutely of the utmost importance at all times. And it's 80% of what we do is all about safety. It's the same with Richard and his design team. It has to be safe. And for us, when we get into the racing, my mission is to get those aircraft, not just to the starting line, but to the finish line. So there's a lot involved. We always have to work with the authorities, and usually they're really excited to work with us as well, because they learn from it. They see the future coming and they want to get involved, and we're one of the catalysts for that. So it's a really great opportunity, and groups like the LAA, are really fantastic in supporting this. I mean, they're really, help us with everything.
So that's absolutely fantastic to hear, and I'm sure that there's a lot of interest. You keep hearing governments dying for new research and new investment in electric tech, electric propulsion tech. If we return to the technical side, there are so many different questions about batteries. So I'll feed one more of those in, and it's about the different battery chemistry types. If there's any limitation on the chemistry of batteries that you're imposing as part of this, or if it's just expected that a single battery chemistry type would dominate at the moment.
I'm going to let Richard answer that in detail, but I will just simply say we don't have specific limitations in the rules on battery chemistry from a sporting point of view. But Richard may want to elaborate.
Yeah, I mean that's a good thing. It's really open, so you have to draw the line somewhere. There's for instance, there's no fuel cell is not in scope. Now that's not, no one really thinks a fuel cell is a battery, but at some point it's a charge carrying system. And the chemistry that you utilize, there may be a boundary there somewhere that someone might nudge against, but really the practical ones that are in scope to get this going are going to be lithium polymer type batteries. There is some new chemistries out there that hopefully we can test and develop based on slightly different chemistries, but they are batteries. And then, as was mentioned before, the supercapacitor stuff. The key thing is that you're going to be having a source of current and voltage, and there's no fuel, involved. So it's non-hydrocarbon and or hydrogen, and you have to charge the battery using electrical charge from the ground, and then it's some form of chemistry. But I think keeping it very open is a great thing, and there is a limited choice in practical terms at the moment. But going forward, you just don't know what really is around the corner in some lab somewhere that can be brought out in prototype form, and then can be put into the aircraft. The aircraft is, for a particular current and voltage on a DC link, it doesn't really matter what battery chemistry you use. Really, the current and voltage is the key on a DC link. So that's opening it up to whatever comes along in the future.
And if we think about the motors that you're using and the batteries and how they're placed, so how does the space envelope that you have for the motors and the batteries compare to all of the existing space requirements that you have for the engine, the hydraulics, the fuel cell, the fuel supply?
Well, so it's a great thing to look at, and there's a lot of scope there for development, and a lot of developers on other industrial type aircraft are looking into this, for even having structural units as the battery packs as well. For our project, we wanted to keep it straightforward at the start, and so we're having independent packs laid out in the existing fuselage. But That's a big limit, and it can be optimized in a lot of different ways. We wanted to keep the weight and balance the same as it was. Obviously, the balance has to be very, very close to the same, and the weight you can play with a little bit. But there are some concerns if you start getting too heavy. You can change the wing area on these aircraft. So you can put a bigger wing. On our cassette, for example, you can design a larger area wing, and you can design a more efficient wing with the planned form and different wing sections, tune it right to the race, tune it to the aircraft weight. You can contain the batteries in the wing if you're building a new wing. Alternatively, at the firewall forward, so the nose of the aircraft where the engine bay is, we are using the existing steel truss mount and then arranging the battery packs around it. That's not necessarily the way to do it. If you develop it more, and you could put an entire new composite housing at the front, which you bolt the motor to directly, and which also contains the batteries and also is the external skin of the aircraft. So you can really optimize that. For our particular cassette, you could also start running battery packs on the fuselage at different places. You run into some problems. You don't want to have long lines for your DC links, and there's extra mass in the cables and so on. But there's a lot of scope for changing the arrangement and the packing efficiency and the structural efficiency of the battery containment. And it's really all open. It's all open to develop. It's how much resourcing do you want to put into it? So our phase 2 project may include some of those features. It most likely would have a different wing because it's relatively straightforward to build one and redesign it and optimize it. And then you can have enough energy so that you can definitely use that full power, that 150 kilowatts for the entire race. And that's going to require a certain mass of battery. And that's going to feed into the all-up weight of the aircraft, and you want to have the wing area and other features balanced. So I don't know if that's the answer, but for sure, you can integrate the battery packs with the aircraft in a variety of interesting and more optimal ways.
And how does the weight of the engine and the motor compare at the moment?
In our case, we're trying to keep it the same. So we want the same takeoff weight as we had before, the same gross weight. And we must keep the balance of the aircraft, so the center of gravity of it, very, very close to where it was. With all of the equipment we pulled out, I mean, we weighed the aircraft and we took the center of gravity of it before we moved anything. Then we weighed all the components we pulled out. And we have a working weight, that we can build to. And that's one of the reasons why we've gone for a relatively small battery in the first instance, is to ensure that our takeoff weight is very, very close to what it was as when the aircraft was delivered. It could go heavier. You could put another 20, 30 kilograms on it. You could run a lighter pilot. So there are those sorts of things to play with. But these things are all part of the optimization of the airplane and then the optimization of it to the race.
Yeah.
Okay. And sorry, go on, Jeff.
Yeah, no, I was just going to say, I mean, that's kind of an interesting, because it's something that people have to consider when they decide how they're going to approach this. So we mentioned that some of these aircraft, the race teams are doing a retrofit, and they're taking an existing plane and retrofitting it with electric. Others are doing ground-up designs. There's advantages and disadvantages to both. And going with a retrofit aircraft, of course, the good thing is you've got an airplane there, you know what the parameters are, you've got some measurements to work within. But by the same token, you have to work within those parameters. So that does present certain challenges. Actually, just think about it. We're actually literally right now, we're reevaluating one of the rules and trying to come up with a better figure for this, because in the Formula One air racing rules, there's a rule about minimum weight, 500 pounds, but that's dry weight. And that means without the fuel tank, without fuel. And in this case, if we say minimum 500, we've effectively got the fuel because it's the battery on board. So really the rule is designed to make sure that people don't make the airframe too light, thereby making it weak and challenge the structural integrity for pulling the Gs that you need to pull in a race. So how do we focus the rule back to getting the structural integrity correct, but not affecting, the weight. So we're having to shift around a lot of different things, and these things occur kind of only as you go throughout the process. I mean, that's a fairly obvious example, but there's a lot of interesting, aspects to that. So.
And obviously, pilot safety has to be a significant consideration, considering the novelty of the racing that you're undertaking.
Always, racing, again, like I said, motorsport, and then you add into that aviation, and then you add into that new technologies. All of the aircraft will be completely new. We even retrofitted, they'll still be effectively a new aircraft and have to be certified as a new aircraft. So there's a lot of variables going on. It's part of our thinking every single step of the way, and it's very important because even aside from the obvious human tragedy of any possible incident, you also you have an incident and that could end the progress of the project. So it's not something we take lightly, and really it's infused in everything we do.
There are so many questions to get through, and there's been such a lot of interest. So unfortunately, we only have time for 2 more. But one of the more interesting questions was comparing this to Formula One. So there were 2 aspects to that. One was whether, because it's there are going to be lots of new designs, whether this enables the pilot and the pilot's skill to have more impact on the results of the race. The other aspect was whether the alternate might happen, where you have a very well-resourced team comes in and manages to dominate in the way that Mercedes has done for Formula One.
Yeah, so certainly, I mean, pilot skill in general is going to have to be extremely high no matter what, just to even get into the series. But when you're talking about what does it take to win, we're trying to find that balance. Your question began with comparing Formula One with air racing, or air race one with air racing. And in Formula One air racing, it's a fixed motor. It's a Continental O200. Richard referenced that earlier. It's a Continental O200. It's a standard motor, and there's very little you can do with it to modify it. That's standard. That doesn't mean that there's not a lot of innovation in airframe and aerodynamics, et cetera, and weight. But it is also a lot to the pilots, a lot to the down to the technology. In our case, yes, it very much could be the technology that just creates such a vast difference. Now, part of that is what we want to see. We want to see, are there technologies that are surpassing other technologies? That's kind of the point of it as well. So that's okay. That's not a bad thing. But we want it to be a race. We want it to be fun. My simple answer to that would be, you're not going to win if you don't have a good pilot. You're not going to win if you don't have a top-notch pilot. So it already takes a top-notch pilot to win. Equally so, the same about the technology. If you don't have a good aircraft, if you don't have the technology, you're not going to win. So it really is the marriage of those two. And why that's exciting is it's not just about one person. It's about really all the team. It's about the engineers. It's about the partners, the suppliers, the managers and the crew chiefs and everybody that it takes to win. And to me, that's the exciting story. So it's all of those things, and we're embracing that. So we think that's a good thing. I think I missed the second part of that question. Sorry.
It was just about whether there would be a very well-resourced team managing to dominate at some point in the future in the same way as Mercedes has done.
Yeah, okay, I'll do that quickly. So that is possible, and frankly, that's a kind of a good problem to have. We're looking for people to come in with investment and try to take it forward. But we think that can be avoided. One of the reasons we chose to base our sport on the Formula One format is that it's really cost effective to get involved. It's really inexpensive, by comparison to motorsports, to actually get involved in this sport. So you don't need to have a big budget to be competitive, and so we think these things are going to go hand in hand as time goes on. So we don't see that as a short-term problem.
And one last question, just slightly left field. There are so many technical that it would be amazing to cover, but it would take all night to go through them. So coming at it from a different direction, one of the questions was, are you considering e-racing without pilots? So basically using AI at some point in the future and racing AIs in electric planes.
Yeah, it's a good question. Actually, I'd be interested to hear Richard's views on this, but just in terms of our strategy, our plans. Let me say there's a loose yes. And what I'm saying is that we're actually, we haven't said this to anyone yet, so you're getting the scoop, but we do have even a new class that we're going to be working on and announcing very, very soon. Even beyond that, we have other aircraft types we're looking at. There's a lot going on in this space, and looking at AI or autonomous vehicles is really, really interesting to us. Of course, we don't want to open it too much too soon, but that very much is an interesting area. I think that the same technology that goes into AI can already, have a place in currently what we do as well. So, it is a natural evolution. So we'll see. Yeah, keep an eye on us and you'll find out.
Yeah, I reckon it's a very nice way to think about development in the future, but it will be a different class. At some point, maybe there would be interest in seeing who can actually ultimately fly around the course better, an autopilot or a person. But there's a lot of development in autopilots, and it's a very good thing. More automation, I think, has to be carefully managed. And it would be an interesting thing to put them up against each other and help that development as well.
Mm-hmm.
Well, thanks very much, guys. That was absolutely fascinating. As I said, there are so many more questions out there. But for the moment, I'll pass back to Rimesh to close out the session.
Thank you.
Great, thank you so much, Matt. Yes, just to echo what Matt has said, thank you so much, Jeff and Richard. Fascinating talk. Like Matt said, we've got a lot of questions, so I'm very sure you'd be able to approach Jeff and Richard throughout their representative organisation website. So they'll be more than happy to answer your questions. Yeah, and once again, thank you so much for explaining the innovations required for electric motors and the entire air racing ecosystem. It's quite fascinating that there's a lot involved. So thank you so much. I'm just going to say, if we were at IET Savoy Place, we'd give you a big round of applause, but I can only do it virtually. So thank you very much for your time. Okay, so if you can see the screen now, our next event is on Friday, 26th March. It's a new class of propulsion, and our speaker is Sophie Harker. And after that, in April, we have the Virgin Hyperloop story, and that's going to be done by the Virgin Hyperloop team, and that's going to be a 6 p.m. start as well online. You can also continue this conversation on our Twitter handle, and we will also be sending you feedback. So please do complete your feedback forms, as we do take notice of your feedback and try and make our events better than they normally are. But here's our Twitter handles again. Thank you very much for today, and have a good evening.
Thank you so much. See you.
Thank you. Bye.